question and answer, and the rest just to hand over. So let's start with Ryan Keeley, and he's going to tell us about testing Lambda CDM with EBOS and SDSS. Please share your slides.
Can you hear me?
Yes.
Okay, great. Hi, hello everyone. I'm Ryan Keeley, a postdoc at CASI, the Korean Astronomy Space Science Institute. I've been working here in Korea for almost 3 years, working on various aspects of cosmology. Today I'm going to be telling you about what we've learned so far about cosmology from the completed SDSS-4 EBOS survey and how it complements the portrait of cosmology painted by other cosmological datasets, specifically in the context of the H0 tension. All right, so the whole point of cosmology is to identify the energy content of the universe that's responsible for the observed cosmic expansion and growth of structure. So starting from GR, we can make basic predictions about how the various constituents of the universe, like matter, radiation, curvature, etc., would cause the universe to expand. So this brings us to the Lambda CDM model, named for its beyond standard model components, lambda for cosmological constant dark energy, and cold dark matter. Ironically, despite being unknown, these components are responsible for the most noticeable features of the universe. By that I mean the current accelerated expansion of the universe is explained by dark energy, and the existence of structures in the universe like galaxies and clusters require dark matter. So of course our jobs as scientists is to test what we think we know about the universe. So to test the lambda part of lambda CDM, to test whether dark energy truly behaves as a cosmological constant, or whether it evolves with redshift, we need to look at the lower redshift expansion history at greater and greater resolution. So this lambda CDM model actually works remarkably well for explaining a variety of data sets. So basically with just 6 parameters and known standard model physics, we can explain a lot of non-trivial physics, for instance, like the production of light elemental nuclei, like in BPN. We can explain how sound waves propagate through the primordial plasma. We can explain how the various components decoupled from the plasma and how that plasma eventually cooled enough such that the photons no longer scattered, as in basically all the physics that goes into the CMB. We can further explain how those perturbations in the plasma grew to be the observed structure of the universe, and further it explains the accelerated phase currently happening in the universe. So my point with all that was that with basically just known standard model physics and just 6 more parameters, the concordance model cosmology can really explain a bunch of really non-trivial physics. So that is until we try to measure H0. So if we take lambda CDM and constrain 6 parameters with the CMB and extrapolate these results to more than over 3 orders of magnitude in scale factor, then we can predict that H0 is around 67.36 plus or minus 0.5. But however, when we use the Cepheid period luminosity relation to measure the distances to galaxies at cosmological distances, we find that H0 is closer to 74. So this tension is becoming increasingly important, basically important enough to recheck everything we think we know about cosmological data sets, either in terms of systematics or intriguingly about new physics. Though the fact that there is no obvious systematics that explains this discrepancy is why I think this is the most interesting question in modern cosmology. Like I said, it could always be the holy grail, new physics. So like I mentioned previously, since the high energy physics at the CMB is very non-trivial, and since lambda CDM does actually do very well at explaining it, it makes sense first to check if any low redshift physics could explain the H0 tension. So low redshift physics, such as things like evolving dark energy, would naturally inherit all of lambda CDM successes with the CMB and can easily accommodate high H0 values. So the crucial test then is to check whether such evolving dark energy models are consistent with the guardrails of the H0 tension, the supernova and BAO datasets. All right, so all right, 1 second. All right, so the EBOS and Pantheon measurements, they're very important in this narrative of the H0 tension, and they're often referred to as guardrails. So they serve basically as a sanity check for potential solutions to the H0 tension. So the BAO measurement measures both dA and H of Z in various, basically as a function of redshift. So with 5 tracers and 7 redshift spins, the BAO data sets from EBOS constraining the expansion history from redshift of about 0.1 to 2.3. Similarly, so interestingly here, all the curves in this EBOS BAO figure, those aren't fits to the data; those are just predictions from lambda CDM. So you can you can tell I guess from the get go that I guess these data sets seem remarkably consistent with each other. So I guess further along, the supernova measure basically luminosity distances. So there's about 1,000 supernova from redshift of 0.01 to 2.3. And one sort of crucial fact is that both of these data sets on their own are unanchored. And so on their own can't basically tell you which value of H0 is correct, either the CMB one or the local one. But they can constrain basically a mutual scale H0 RD. And I guess beyond that, they also constrain basically the shape of the expansion history, even if not the scale. And so can hence basically do the interpolation from redshift of 0 to redshift of Z star. Okay, so my strategy with any sort of new kinds of analysis, these new kinds of analyses, are to try to be as complete as possible. So if we have this tension between lambda CDM physics constrained at high redshift and the local expansion rate, then my strategy is to try to be as agnostic as possible in the search for any sort of lower redshift physics, namely curvature or evolving dark energy, that might resolve this tension. And so, but by being very agnostic about the nature and evolution of dark energy, we can be complete, as in if we conclude that there is no parameterization that can solve it, we can basically be robust in saying that there is no lower redshift solution to the H0 tension. So to be specific, I'll be talking about three sort of cases. First is the relatively familiar curved CPL parameterization here, where and it's sort of important to emphasize that any evolution in this model, basically any evolution in the dark energy equation of state, basically occurs at redshift 0. And so to generalize this last fact, to allow for evolution in the dark energy equation of state at any redshift, we also parameterize the dark energy equation of state with a series of Chebyshev polynomials and their corresponding coefficients. Just to be a bit clear about this, since the C1 value is, since the first Chebyshev polynomial is flat, lambda CDM in this case would correspond to 1, 0, 0, 0 in a space. And so so further, I also use GPU regression to reconstruct the distances and expansion history that these guardrails want. So GP is useful basically since it's a non-parametric or model-independent method, and thus it's flexible enough to find surprising results like unknown unknowns should they exist. So I guess allow me a bit of a brief aside to talk about GPU regression, since it's sort of my pet inference technique, and I do think it can be useful for everyone. So to say what the Gaussian process is, a Gaussian process is a random distribution that generates a function as opposed to a single number. So this distribution of functions is characterized by a covariance matrix shown here, which in turn is parameterized by a set of hyperparameters, which determines how much the generated functions differ than the mean function. So the sample GP draws can be thought of as a hyperfunction. It generalizes like the expansion history of the universe to something beyond lambda CDM. And by that I typically mean I choose lambda CDM, a lambda CDM expansion history to be the main function in my analysis. And so the regression part of GPU regression then involves training these samples based on how well they fit the data. This whole process can be summarized by the Bayes equation below, where if you have a random h of z function in hand, it's easily enough to calculate a likelihood. Then we can marginalize over the infinite dimensional function space of the Gaussian process by just sampling functions. So the primary utility of GPU regression is to test whether the data are consistent with the input mean function or whether there's additional information in the data sets. So essentially, by calculating the posterior of the hyperparameters and then seeing if sigma f in particular, the parameter which controls the y-axis of the deviations away from the mean function, is consistent with 0. So for an arbitrarily small sigma f, the Gaussian process will generate expansion histories which are arbitrarily close to the mean function. And so if this whole process prefers a sigma f equals 0, that's an equivalent statement to saying the data prefers something beyond lambda CDM. So basically, if we are a bit clever and choose the best fit lambda CDM model to be the mean function, thus thus we can start to make robust statements about the entire lambda CDM model as a whole. So if the data prefers something better than the best, then everything in the model can be rolled up. However, a bit disappointingly, perhaps, that doesn't seem to be the case with existing data. So what we see here is the posterior, the hyperparameters, where the color corresponds to the delta log posterior, and the white lines correspond to 1, 2, 3 sigma confidence levels in the solid dashed and dotted. The data used here are the Pantheon supernova and SDSS BAO datasets, and the mean function is the best fit lambda CDM extension history to both datasets. And so thus that you can see that the 1 sigma contour is basically consistent with 0, or 0 is within the 1 sigma contour. Then we can conclude that lambda CDM is consistent with both joint datasets. That's not to say that lambda CDM is the only thing allowed. So there's a fair bit of flexibility that's still allowed by these datasets. So in these figures, the blue bands specifically correspond to 1 and 2 sigma confidence regions from the Gaussian process, and the orange corresponds to the same, but for the lambda CDM model. So you can see that for the supernova and BA datasets, they still allow for flexibility beyond lambda CDM, but perhaps don't prefer it. This plot is specifically H of Z, the shape of the expansion history. So since GP alone doesn't really have enough information to make full use of the CMB, so here I'll focus on the curved CPO parameterization and focusing on that as a possible explanation for the H0 tension. So in this figure, we see in olive and navy colors, we see constraints from H0 RD from the BAO and supernova datasets. As with the case of GP, generalizing the lambda CDM case, in this case the curved CPO, increases the size of the constraint. And in green here, we see the shoes constraint on H0. So the common story for these kinds of plots is that since the CMB constraints are dragged so well to merely a fraction of percent, the 3 data sets, the CMB notably are drag, the BAO plus supernova in these diagonal contours, and H0 here. So typically they create a triangle where at most 2 of the 3 can be satisfied. And that narrative is borne out if you look at the lambda CDM best fit to the Planck dataset, which you can see here in red. However, you might be a bit misled if you looked at the curved W0 WA case. So you might think that there's this whole region here where the olive overlaps with the orange, with the gray, which overlaps with the green. So you might think that any of this parameter space is a reasonable solution to the H0 tension. But it's important to remember that why the are so blown up is because the extra degrees of freedom generated by these models are basically correlated with H0. And the 2 different data sets, like the CMB and the Lorentz stuff, their degeneracies exist in different directions to each other. So basically, when you do combine even the curved CPL parameterization using all 3 data sets jointly, because the different degeneracies for them individually exist in different directions, they basically, when combined, reduce to a very small region around the lambda CDM case, which you see here in blue. So even though this region might look to be reasonable, a reasonable fit to all legs of the triangle, basically when you actually look at the joint constraints, then it's sort of reduced to this relatively small region, and most importantly, the H0 constraint is outside of it. So this is indicating that this curved CPL parameterization isn't a great solution to the H0 tension. And similarly, though it's not shown here, it's basically the same categorical case for Chebyshev. The specific details of this apparently don't seem to aren't particularly sensitive in how you parameterize any sort of evolution in the dark energy equation of state, just that it evolves at all. So I like this plot because it shows basically sort of I think it alone sort of contains a bunch of the narrative around sort of the H0 stuff. So zooming in, so this is the curved CPL case where we see the posterior for omega matter and W0, and these are probably the most important parameters to talk about the H0 tension. And I guess I want to explain why the degeneracies exist along these directions. So to explain the figure, the red is the 1 and 2 sigma confidence region for this case, and the color here is H0. So I guess to explain why H0 is correlated with omega matter for the joint CMB plus BAO plus supernova data sets, So basically everything in the CMB, each of the different L modes are roughly independent of each other, and they're roughly independent. Sure. Second to last slide. And they're basically independent of any of the low redshift physics. So you could say that omega matter h squared itself is basically a model independent constraint, and it's basically it's independent of basically any sort of low redshift physics. So if omega matter h squared is robust, if any solution were to increase h naught, that would necessarily come with a decrease in omega matter. So that's why I guess the left-hand side of the spot is yellow as opposed to dark blue, or why there is a gradient at all. And so similarly, why h naught is correlated with a phantom sort of dark energy. So basically, like similar to omega matter h squared, which is basically a constraint on, which is basically just coming from the third peak. The first peak tells us what theta s is, and if there's no new high redshift physics, that's basically just a constraint on dA of z star. And so if you were to increase h naught, then that would necessarily decrease dA of z star. But if you have a phantom case, then that then decreases h of z at intermediate redshifts, basically enough to leave dA z star unchanged. And so that's why, and so that's explaining why, again, the bottom part of this plot is correlated, is more yellow than the top part, why there's basically any sort of high H naught solution or higher than 67 requires some sort of phantom type of thing. Okay, so that basically brings us to our conclusions, which is so I guess the important parts to emphasize are that the supernova and BA alone have large degeneracies in their extended parameter spaces, and the CMB does as well. But I guess they're sort of in opposite directions. Further, each of these data sets seem to be consistent with each other, and so can be statistically combined. But even though there is no preference for curvature or evolving dark energy, there are still large swaths of parameter space that are interesting and still allowed. And despite this, that the BAO and supernova are in stark tension with the Schu's H naughts, even in these sort of lower redshift extended parameter spaces. And I think, so basically because curve CPL and Chebyshev polynomials, because they all basically can't constrain, basically don't offer a real solution to the H naught tension, I think it's basically robust to conclude that there is no low redshift solution that can solve the H naught tension. Perhaps there exists a high redshift one, but I mean, all that physics is very non-trivial. So I guess if gun to my head, I guess I would say that it kind of has to be a systematic, probably in the Cepheid part. Thanks for your time.
Thanks, Ryan. Very nice talk. Do you have any questions? If you raise your hand or put it in the chat. I don't see anyone. Then
can I ask one question, Chris?
Yes, please.
Ryan, the paper in preparation, why you put PRL? Are you that confident it will be PRL?
Yeah, I mean, you want to manifest the results that you want to see in the world, right? So yeah, so being
good luck with it.
Overly optimistic, but yeah.
Okay, good luck with it.
Okay, then,
well, right. So I mean, that's a subtle technique to get people to pay attention, to look for those sort of things.
So I have a quick question.
Sure, yeah.
So this isn't the first time we've had Hubble tension in cosmology. It goes back many years. And I guess at that time, they also spent a lot of, they had held workshops and they debated and they were serious. And now we look back and we think, okay, they got it wrong, their error bars were too optimistic. How do we know that that's not happening now? Maybe that's a difficult question for you to answer, but could it just be as simple as that, just that the way science is done, we're driven to be optimistic in our error estimation? I
guess I'm not entirely sure what you're asking. I mean,
I'm just saying, if all experiments they report their observables, and you just multiplied their error bars or their contours by a factor 1.5 to, I'm guessing all the tensions disappear.
I guess. so yeah, I mean, so I mean, I guess if I mean, I guess it is always possible that like 3 sigma errors, 4 sigma errors, they will eventually happen. So yeah, it could easily be the case that this might be just a random fluctuation. I mean, I think that's basically how to interpret your question. That I mean, there is no way to be like at one moment sure that any sort of data set isn't just a random fluctuation, any tension isn't just a random fluctuation. But I mean, I guess by collecting more data, like I think specifically with Gaia and eventually with gravitational waves and with strong lensing, I mean, those are all independent of any sort of Cepheid stuff, and any sort of Cepheid calibrations. And so if it is just a random fluctuation, it will be in those. So I mean, so I guess it's, so I mean, as far as that question, I think we just have to wait for the answer.
Yeah, that sounds good. So thank you. Thanks again, Ryan.
Sure. Thanks for having me.
We'll now move on to Hanno. Yeah, thank you.
Hello.
Can you share your slides, Hanno?
Yeah, sure.
So I'd like to welcome Hanno Ku, and he's going to tell us about cosmology with type 1a supernovae. Please proceed, Hanno.
Oh, sorry. Thanks. Okay. I wish to thank organizers for giving me a chance to present our recent works. One second. My name is Hanno Ku. I'm working with my supervisor, Professor Arman Shapierlu, in Korea Astronomy and Space Science Institute and University of Science and Technology in South Korea. I'll talk about our three recent papers with the title of Cosmology with Type 1a Supernovae, Searching for Systematics and Model Independent Reconstructions. For more detail, please see 3 papers on the slide. First, I'll give a brief introduction about the studies. Type 1a supernova, in short SNE1A, are used as standardizable candles with the distance for distance measurement, and have become one of important portion of modern cosmology. However, the standardization is purely empirical and requires Likert fitting model with a number of parameters and hyperparameters. The Likert hyperparameters are usually constrained based on assumption of cosmological model, but we can find the model-independent manner to constrain the hyperparameters. To search, in addition, to search for systematics in the SNE1A data, model-independent reconstruction is required. After reconstruction, we can look for features in the data which can be a hint for systematics or new physics. We can also perform model selection and parameter estimation without comparing models. To do all of this, we will apply the iterative smoothing method, which is the non-parameter method to reconstruct distance modules and its expansion history of the universe. It is introduced by Shapierlu et al. In 2006 and improved by following papers on the slide. This method starts from initial guess of distance modules, but generates model-independent reconstructions of distance modules with lower chi-square value after numerous iterations. We can find equations for each iteration on the bottom of the slide and more detail in the paper. Next, to construct the distance modules from the data and use them for constraining the Likert hyperparameters, we use the joint Likert analysis compilation, in short, JLA, which have Likert parameters information based on Salton theory, and apply the tree formula, which is shown on the middle of the slide. Among the parameters of the formula, 2 proportional factors and 2 absolute B-band peak magnitude parameters, alpha, beta, large MB1, and delta M, are Likert hyperparameters that need to be constrained, while others are just Likert parameters provided by JLA. We assume 3 different cosmological models for the analysis. One is lambda CDM, lambda cold dark matter model, which have equation of state parameter equals to -1 for all redshift. Another is CPL, Chevalier-Polarsky-Linder parameterization, which parameterize the equation of state parameter at low redshift, as shown on the slide. The other is PEDE, phenomenologically emergent dark energy model, which claims no effective presence of dark energy in the past, then emerges at later times. This model is is introduced by Lee, Shapiro, 2019. We compare hyperparameter constraints of the three models with three different colors with those from the reconstructed distance modular, like colored in red. As we can see on the right corner plot, contours are all consistent with each other, which indicates there is no dependence on cosmological model. One exception is that large MB1, one of absolute B-band peak magnitude parameters from reconstructions, shows uniform distribution because SNE1A alone cannot constrain an absolute distance scale. Next, we divide the data into two redshift bins with equal sizes and compare the constraints from the reconstructed distance moduli. We can see that statistical deviations between the two contours are not large enough, which indicates that there is no clear redshift evolution. Based on the equations on this slide, we have derived the expansion history of the universe and two parameters which describe dark energy properties of reconstructions with higher likelihood than that of the best fit lambda CDM model. We adopt the Ohm parameters introduced by Sani, Shapiro, and Starobinsky in 2008, since it is equal to the matter band density at present time when background model is a lambda CDM model, which indicates that it can be useful to test the lambda CDM model. And on this figure, top left panel shows relative deviation of 8,000 reconstructed distance moduli from the best fit lambda CDM model with a constant shift, while others show reconstructions of the other parameters derived from them. We have produced 20 reconstructions from each of the 4 different initial guesses, and each of 100 random light curve hyperparameter values. We find that reconstructions are consistent with the prediction of lambda CDM, and more importantly, allowing some additional flexibility. And from now on, we talk about looking for features in SNE1A data using the more recent Pantheon data. We find oscillating features in the Pantheon data at redshift lower than 0.5 around the best fit lambda CDM model. We have tried to see how generic such behavior is found at many Monte Carlo realizations of the data using the full covariance matrix of Pantheon data. On this table, the two circles shows that the deviation of the redshift bin best fit parameter values from their full dataset best fit values are larger than or comparable to 1 sigma, which indicate oscillating features. Such features occur in 4 to 5% of Pantheon-like simulations. And we think that it might be a hint to possible systematic or new physics. Finally, we talk about direct model testing. We do this because model testing using Bayesian evidence depends on comparing models. We try to test consistency of a model and the data without comparing different models by estimating likely distribution of delta chi-square using iterative smoothing method for model selection and parameter estimation. For this analysis, we assume lambda CDM, Pede model, and the kink model, which introduced by Khorasanity and Copeland in 2003. Based on previous works, we select certain model parameter values that's shown on the bottom of the slide as an example. You can see those previous works at the bottom, on the bottom. So for model selection, we define delta chi-square as chi-square difference between smooth reconstructions and model best fit initial guess. Remember that the iterative smoothing method starts from initial guess. We can see that likely distribution of delta chi-square for 3 different model best fits using 1,000 Pantheon-like mock realizations based on 3 different fiducial models are the same with each other, which indicates no dependence on cosmological models that are used for simulation. And for parameter estimation, we use the fiducial model as initial guess for defining delta chi-square. You can see that the definition of delta chi-square in the red circle is slightly different from the previous one. In this figure on the slide, we can find that the likely distributions are the same with each other, which indicates no dependence on cosmological model again. And this figure shows estimated constraints on matter density at present time for 3 different models using 95% confidence limits from Pantheon. We can see that they are highly distinguishable with one another. Next, we perform model selection with future data, which is 1,000 forecasted W1st mock realizations based on lambda CDM fiducial model. Note that the official name of W1st has changed to Nancy Grace Roman Space Telescope. As shown on the figure and table on the slide, the likelihood distributions for the 3 different models and their estimated type 2 successes, which indicate the numbers of cases that the wrong models are ruled out beyond 95% or 99% confidence level and limits, are highly distinguishable from one another. Now, here I summarize that we find no model dependence, no residue evolution of life curve and hyperparameters, and find that reconstructed expansion history and dark energy properties are consistent with prediction of lambda CDM, allowing some additional flexibility. We also find that about 4 to 5% of Pantheon-like simulations have similar oscillatory features in that in the Pantheon data, which might which might indicate systematics or new physics. Finally, we show that model selection and parameter estimation using the iterative smoothing method works well, which might confront with Bayesian analysis in the future. And this is what our paper in preparation is about. Thank you for listening to our talk. Questions and comments are always welcome. And for more detail, please see the papers on the slide. Thank you.
Thanks, Hanno. That's a great talk. Do we have any questions from the audience? Can you go back? You said you find different omega matter. Can you say more about that? You can differentiate omega matter. Like you're muted. Yeah.
So are you talking about this slide?
Yeah. So what's going on here?
So we try to estimate parameter value of matter density at present time from 3 different models using the likelihood distribution method that we introduced in this part. I can see that there is one question.
Yeah, one question. Any updates about dark energy survey and release new data?
Dark energy survey.
DES.
DES. Okay. At this moment, there is no update using DES yet, but I think that can be one of our future work.
Can I have 1 minute to comment, Lito?
Yeah, please. Yeah.
Okay, so about the slide of the matter density, these 3 dark energy models are substantially different from each other. So, the line, the dashed line in the 100 slide, is basically means that the range of the matter density, which is allowed for these different dark energy models for the data that he has used. So that practically shows if there is another data which can be basically perpendicular to this data that he used, these models can be distinguished, because for the case of the kink model, for example, it prefers very low matter density, for the lambda CDM around 0.3, and for the PEDA larger values. But these are the allowed region that these dark energy models are allowed within their own flexibility.
Okay. So then you want to get omega matter from a different probe, maybe lensing or something?
I mean, if the other data combine, things become better. So yeah, the first paper was mainly to proof of concept to use this approach to define the likelihood function and do the model selection. But yeah, if we include more data, probably, there would be much more power to distinguish between different models.
Interesting.
Yeah.
So if there's no more questions, then I'd like to thank Hannah again. Thank you.
Thank you.
If you stop sharing the screen. And next speaker is Priyanka Sarma. Can you
Yes.
can
Hi.
you share? Hi.
Yeah, sure. Can you see my screen?
It's coming, I think. It's a little bit small.
Yeah. Can
Yeah.
you see my screen now?
Yeah, that's perfect. Yeah.
Okay. Yeah.
Okay.
Okay.
Please start.
Yeah. So, hi everyone. So I'll be speaking on a recent work which is on the broadband 21 centimeter cosmological signal from dark matter spin flip interactions. So when we look back at the history of the universe, we find that there is the universe was for a period of time it was neutral, and there is no source of light coming from this age or this phase of the universe, and this is called the cosmic dark age. So what exactly happened during this dark age is still an untested mystery, and many experiments are trying to probe this phase of the universe with and particularly the 21 centimeter experiments are trying to probe this phase of the universe with the hyperfine transition of the neutral hydrogen. So the neutral hydrogen could be a very good tracer of what exactly the baryons are doing in that epoch of the universe. So here we have this signal, which is known as this global 21 centimeter signal, which arises due to the hyperfine transition in the neutral hydrogen, and that can tell us about the history of the universe, particularly the unknown period of the formation of the first stars and the galaxies. So let's first see what is the expected behavior of this 21 centimeter signal in the standard cosmology. So here we have some kind of relative intensity, which is known as the brightness temperature. So I'll talk about this brightness temperature in the later slides, which is shown against the frequency at which the 21 centimeter radiation is being measured and the redshift from which it is coming from. Okay, so as we go back to early time, that is to the higher redshift, we see some kind of absorption in this 21 centimeter radiation, followed by a second absorption deep, which starts as the formation of the first stars and galaxies starts forming, and then finally a possible emission line, and finally the signal disappears as the universe gets reionized. Okay, so for the moment, this 21 centimeter line is quite exciting, as it can tell you about the unknown things of this the dark age. And as I mentioned, there are many experiments which are looking for this, and very recently there is a report from the AGS collaboration which has reported an absorption profile which is centered at the 78 megahertz in the sky average spectrum. Okay, so what's interesting thing about this observation is that the absorption dip they have observed is in the same ballpark region, same ballpark of the frequency that is also expected in the standard cosmology, which is around the 70 to 80 megahertz. But what is surprising about this observation is that the amount of absorption they have found is almost 2-3 times higher than what is expected in the standard cosmology. So this report has got much attention, and much work has been proposed to account for this anomalous absorption dip. So motivated by this, in our work, we ask the question whether there are models that exist perhaps in the beyond standard model of particle physics or beyond standard model of standard cosmology that can explain the predicted 21 centimeter signal and also could be tested in future experiments. And in our work, we propose such a model that shows a distinct 21 centimeter absorption line and which is completely unlike what is expected in the standard cosmology. So before going to our model, I'll briefly talk about the origin of the 21 centimeter line and few useful parameters. So as you know that the interaction of proton spin and the electron spin in the ground state leads to the splitting of the ground state to a singlet state and a triplet state. And this splitting of this ground state is known as a hyperfine splitting, which is of the order of delta, which is of the order mu electron volt. So the transition from the triplet state to a singlet state, it leads to emission of radiation of wavelength 21 centimeter or equivalently or radiation of frequency 1420 megahertz. Okay, so now for a collection of hydrogen atoms, the number of hydrogen atoms in the excited state and the number of hydrogen atoms in the ground state can be parameterized by a single parameter, which is known as the spin temperature, and the parameterization is given this way. And the spin temperature, which plays a very key role, it has a one-to-one correspondence with the effective temperature known as the brightness temperature, which is defined as the difference between the measured intensity of 21 centimeter radiation and the expected intensity of CMB derived from the black-body law. So you can see that this delta TB or the brightness temperature, it is proportional to the difference of the spin temperature and the CMB. And the reason for this proportionality is that the spin temperature, which controls the relative population of the spin states, if it is exactly equal to the CMB temperature, so what does it mean? That the spin states are exactly in thermal equilibrium with the radiation that is passing through it. So we don't. So in that case, we don't expect any kind of absorption or emission of CMB photons by the neutral hydrogen, and we don't expect any kind of signal, absorption or emission signal. But if the spin temperature is higher than the CMB temperature, which tells you that there are more number of hydrogen atoms in the excited state, so this will give you a positive signal, or it will give you a net emission signal, net emission of the CMB photons. Then if the spin temperature is lower than the CMB temperature, we get a absorption, we get a negative brightness temperature, and hence we get a which corresponds to a net absorption or absorption signal. Okay, so there are the main takeaways from this is that first, the spin temperature is not necessarily a measure of the kinetic energy of the gas. Rather, it's the measure of, it gives you the relative population of the spin states. Secondly, depending upon the sign of the brightness temperature, we'll get a absorption or a emission 21 centimeter radiation. So now one asks what are the mechanisms that affects the spin temperature and how to determine the spin temperature. So to do that, one start with this rate balance equation, which equates all the excitation and the excitation processes, and the various mechanisms that can affect this spin temperature are, for one, due to the excitation and re-excitation process due to CMB. And again, there are the collisional excitations or the collisions between collisions of the hydrogen atoms that can also cause this excitation and de-excitation process. And finally, the excitation and de-excitation process due to the Lyman alpha from the first stars. So with this, one can get a simple algebraic equation which connects this spin temperature to the CMB temperature, the gas temperature, and the color temperature. So basically, to know how this absorption signal or how this brightness temperature evolves with the redshift or time, we need to know this spin temperature, which tracks this brightness temperature, how exactly it evolves with the redshift. And in a way, to know that, to know this evolution, we need to know the evolution of all this temperature and the couplings appearing over here. Here show the evolution of spin temperature that is expected in the standard cosmology. So you can see that various temperature that is shown with respect to the redshift 1 plus Z. So you can see that the spin temperature, initially it was tracking the gas temperature because of very high collisional coupling. But once the collisional coupling drops below the CMB-induced coupling, which is of order 1, you can see that the spin temperature gets pulled towards the CMB temperature. And then once the Lyman alpha coupling turns on, the spin temperature again pulls down towards the gas temperature. And finally, because of the X-ray heating, it again starts following the gas temperature. So we can see two regions where the spin temperature drops below the CMB temperature, and hence we get two absorption dip, one at the high redshift and one at the lower redshift. So the main point is that in the standard cosmology predicts two absorption dips, one at the higher redshift and other at the lower redshift, because of this collisional coupling and the Lyman alpha couplings. So in our work, we try to make prediction about the distinct 21 centimeter line, which arises due to the dark matter spin flip transition, interaction. So the basic idea of the model is very simple. And the idea is that apart from or in addition to the various mechanisms that can affect the spin temperature, we introduce new interaction of hydrogen that interacts with this dark matter via this axial vector. That can directly flip the spin of the hydrogen. So this the model contains 5 parameters. So we have these couplings and the masses, and also the fraction F, which stands for the fraction of dark matter. So this model comes with two distinct effects. One is that it can directly change the spin temperature via the processes, excitation and de-excitation processes of due to this dark matter spin flip interaction, and also it can affect the kinetic temperature of the gas via the energy exchange of the hydrogen and the dark matter. And we have it did a very detailed calculation involving the bound state of the hydrogen and the dark matter and what we got is very simple, is that the scattering cross section or the spin flip scattering cross section is inversely proportional to this hyperfine splitting parameter delta square. So what does it tell you? So this tells you that it is possible to get a very huge cross section even for a very small coupling of alpha E and alpha chi, because of this tiny splitting parameter that is sitting in the denominator. Again, we have also calculated the energy transfer cross section, which now gets a separation factor of again this delta and a new temperature scale, which is T effective, and which is a combination of this Tk and Tchi. And for sufficiently low mass of dark matter, this T effective can be as low as this the dark matter kinetic temperature of dark matter, which is expected to be very cold. So now, in addition, in presence of this additional interaction, which is this dark matter spin flip interaction, the modified spin temperature, now it gets a new contribution from the term, which is one is given by this xt, which is the spin flip rate, transition rate, and which can be very large even for a smaller coupling, and a new temperature scale with T effective, which can be as low as the dark matter temperature. And we have considered a range of parameter space of the model, and depending on the strength of the couplings, we have split it in the parameter space into 3 regimes. One is the strong, intermediate, and weak coupling. So let me show you some benchmark plot. This benchmark plot is for strong coupling, and let me focus on this particular plot where we have plotted the spin flip transition rate and the collisional coupling rate, which is shown in the red line. So you can see that the spin flip transition or spin flip coupling is very huge for a large period of time, and it's dominating over any other coupling that is present over here. So and then you can one can also see how this the dark matter temperature and the gas kinetic temperature evolves, and hence the spin temperature evolves with the redshift. So all this leads
1 minute
to
left.
Yeah.
1 minute.
Okay, all this leads to a very distinct 21 centimeter line, which is very different from what is expected in standard cosmology and excess gas cooling model. So here we get a very strong broadband signal that expands over a large range of frequency. So this scenario changes a little bit when you go to the weak coupling benchmark point, where you can see that the coupling, the spin flip coupling, once it drops below the CMB induced coupling, we get a rise in the 21 centimeter absorption line. Okay. Then we have considered a variety of constraints, and both laboratory and astrophysical constraint, and found that a large portion of our parameter space is safe from this constraint. So here I would like to summarize by pointing out some key results. So, so in our model, we have predicted a very strong single broadband absorption line, which expands over a large range of frequency. And which is completely different from what is predicted in the standard cosmology and the excess gas cooling model. And the reason for this strong and broadband signal is because of the strong or the huge spin flip transition rate and the new low effective temperature. And another interesting thing that you have found is that in the weak coupling regime, the spin temperature does not necessarily track the gas temperature. So it's very interesting, because now one can test this mechanism with the independent probe of the gas temperature in this regime, if one could come up with such an probe for the gas temperature. Yeah, thank you.
Thank you, Priyanka. Very nice talk.
Yeah, yes.
Do we have any questions from the audience? Well, there's a question in the chat that says,
yeah, sure.
Jiajun Zhang asks, will such interaction change the structure formation process?
Sorry, okay.
There's maybe another chat, it's Q&A chat.
Okay, yeah. Structure formation process. So okay, so I'm not fully aware of. I mean, we haven't considered how it could actually change the structure formation process. Okay, I think I have to think about it. Yeah.
Yeah, I guess just expanding on that, I guess you could imagine these interactions that you're considering may change these bubble formations that are happening during reionization. Some kind of spatial distribution of these bubbles and things may be affected.
Okay.
But yeah, interesting. Are you considering other experiments like SKA in the future? Are you making constraints for those predictions?
Yes. Yeah, so like we have predicted, I mean, we have given some testable predictions that can be like verified in the future experiments, which will be mostly led by. So the more details of this can be found in actually in the paper. Yeah.
Okay, thank you. If there's no more questions, then let's thank Priyanka again. Great talk. And can you
Thank you.
Yeah, thank you. And is Hassan Ibrahimian there? Can you share your screen, share your slides? I don't know. Hassan Ibrahimian, are you there? Yeah. Great. And can you unmute yourself?
Can you see my desktop?
I can see the slides and I can hear you. Yes, perfect. So
okay.
I'd like to introduce Hassan Ibrahimian. He's going to tell us about dynamical tidal locking. Please take it away.
Okay, I would like to thank first from the organizers to giving me this opportunity to share this with the audience. I'm going to talk about the dynamical tidal locking. It's a new source for the spin of the dark matter halos. I've done this work under supervision of the Ali Akbar Abu Hassan. He is my supervisor, doctoral advisor, of course, and this is part of my PhD thesis. And you can see some details in the mentioned article, and I tell you all things about this. We're starting with the question of what is the origin of the angular momentum of the galaxies or dark matter halos and how it evolves. Why is it important to know this, to answer these questions? First of all, it's part of the structure formation theory. If we want to talk about how structure forms and how they evolve, we need to know their angular momentum. Their angular momentum play a crucial role in this story. And more importantly, lensing surveys are sensitive to the alignment of the galaxies. Shape of the galaxies are determined with their angular momentum, and their angular momentum may be correlated to the structures. Of course, there have been observed some correlations between the angular momentum and the structures. In the picture you see, more massive halos tend to be perpendicular to the filaments in the cosmic web, and low mass halos tend to be aligned with the filament of the cosmic web in the cosmic web environments, of course. There are many studies. I mentioned one under the picture, under figure. Very well known theory and very well studied, known as tidal torque theory, explain the origin of the angular momentum. It's very simple. If you assume the tidal tensor, tidal fields, gravitational tidal fields, when a matter wants to collapse and form a halo, if you calculate the effect of the ambient matter tidal fields, you can see that there will be an angular momentum for the final halo. When a halo collapses, it collapses in the gravitational tidal field, of course, and this tidal field exerts an angular momentum on this. I've shown you some of the detailed calculations with the Zeldovich approximation. You can write the position, physical position of dark matter particles in terms of the Lagrangian co-moving coordinates and the displacement vector, and simply you can show that the density contrast of the matter of the dark matter particles are proportional to the nabla of the potential over some factors. If you calculate more detail, you can show that there is a growth factor B, which is the function of time, and something that is constant with the time. So, at least for the linear era, at least when the halos are linear. By this assumption, you can calculate angular momentum of a region, of a Lagrangian region, that you think it would be a halo at the later times. And if you write its angular momentum, you find a inertial tensor, which is this integral, and a tidal tensor, which is this tensor. Both are independent of the time for the initial times, for the linear times, when the proto-halo, when we have proto-halo and it is in its linear region, and some factors that are function of the time, a scale factor multiplied by the derivative of the growth function. And this is the prediction of the tidal torque theory. And it has some predictions that will confirm. If you explicitly calculate this a squared that multiplied by time derivative of the growth factor, it is exactly equals to time in the matter-dominated era. And many simulations have confirmed that if you find a halo at the present time, trace back its particles to the earlier times and see and measure the angular momentum of the particles at that time, you see that it grows linearly with the time. Or and in this picture of White in the 1984 and Lopez in most later times confirmed that this is the case for the proto-halos. But if you notice that the tidal torque theory is just regarding the first question, it's just answering first question and leaves the second question, that how it evolves. After the halo formation, after the halo forms and we have a compact object, its angular momentum is conserved and it doesn't change with time. And so the tidal torque theory says nothing about the evolution of the angular momentum. We think that it's quite well for the formation, for the origin of the angular momentum, for the initial angular momentum of the halos, but not for the evolution of the angular momentum. One possible solution for the evolution of the angular momentum is taking measures into account, as some people did, but there are some subtleties here we are mentioning. Then, the other evidences for that tidal torque theory isn't enough is the spin direction of the tidal torque theory gives you an analytic expression for the predicting both direction and the magnitude of the angular momentum. Of course, you can calculate the tidal fields in the simulations. You can calculate the inertial tensor. The other things are quite well known, and you can predict the direction of the angular momentum of the halos. And almost always the spin directions deviate from the TT predictions. I showed you some studies that indicated that, but there's much more other studies, and it's established results. On the other hand, the mergers I mentioned that could possibly change this story, it is somehow within the picture of the tidal torque theory. If you think about the mergers like the mass accretion, tiny mergers, it's like the mass accretions, the tidal torque theory can still predict the final angular momentum even with the mergers, because if you have a halo with this merger tree, you can the final halo's particle are some particles that merged with in the merger history, or in other words, And the same tidal field that accelerates the halo particles, it's also accelerates the halos which merge with each other to form a final halo. So mergers are somehow like tidal theory. It's nothing much more different. There's a study I mentioned here. It shows that if you change the initial conditions so that the calculation of the tidal torque theory have remain constant. I mean, you change the angular momentum, you change the particles' position or velocities, but the expression on the tidal torque theory remains constant. The final angular momentum is also constant, even with the mergers. So somehow the angular momentum is encoded in the initial conditions. Our proposal to predict the evolution of the angular momentum is tidal locking theory. Tidal locking is well known in the solar system, in the planetary systems. The moon is tidally locked to the Earth because of the gravitational effects, gravitational tidal effects. The idea is that when two halos passes by each other, by flyby or anything, their angular momentum changes with this estimation. Also, the detailed calculation confirms this estimation. And f is some numerical factors order 1. It's something like 2/5 or something like 1/5. But we set it as a free parameter. It can depend on the shape of the halo and the orientation of the halo, but it's some number just like 1/5 or 2/5. For example, for a completely spherical halo, this f is equals to 0 because spherical halos doesn't feel the tidal fields. We checked this with illustrative simulation. We picked 3,000 halos in the illustrative simulation at the present time at the redshift 0, and traced them back to the redshift 9. We looked to their angular momentum change. We calculate it can be read from the simulation, the total angular momentum change. We estimated the tidal torque theory effects, the tidal torque theory contribution to the angular momentum change, and we subtracted from each other and get something that we believe that it is anything other than tidal torque theory, and it's a summation of the other effects from tidal torque theory, the net angular momentum subtracting the tidal torque theory. And on the other hand, we calculated the tidal torque theory portion of this from the theory. This is the free f parameter, and by fitting these two with only one free parameter, we find that with f something like 1/4, these two remarkably coincide. This tidal torque theory from the theory is denoted with blue line, and the above that we read just from the simulation is then denoted by orange line, shown by the orange line, and these two are remarkably coincide. We published this last year we published this result in detail. You can go and see read from there. And these gray graphs you see at the background, they are individual halos. We just averaged. We just calculated their average. These ripples in the graphs, you see that sometimes they are something like this, something ripples like this. It is because the two successive snapshots have the little time interval. The duration, the time interval between them are too short, and the angular momentum change drops at that snapshots. so far, we have, I've told you anything that we published before, but from now on, I'm telling you the new results we have. We haven't published them yet, but we are trying to do in a few days later. The alignment of the TTT and TLT can be checked. It's not hard to show that with the tidal torque theory, the angular momentum, if you average out the shapes, the mean angular momentum tends to align with the second, with the middle eigenvector of the tidal potential. I mean, cosine theta is L dot P2. P2 is the second eigenvector of the tidal potential. At the earlier time, this is the case. The halos tend to align with this, but at the later time, at the present time, these alignments wear off. On the other hand, TLT, our mechanism, predicts that alignment. I'm just with the calculations telling you results. At the TLT states that the alignment of the angular momentum tends to align with the vector velocity, with the velocity of the halo. And it can be simply read from the simulations, and we see that this is the case for the, this is the result for present time. In the present time, there's little but significant, statistically significant alignment between the angular momentum and the velocity of the halos. And
one minute.
Okay, I'm finishing. I'm just finishing. And this is the same results at the redshift 6. You see that such alignments disappears because it's too early to TLT to act. If TLT needs time to align and change the alignments, and at the present time it can be changed, but at the earlier time it hasn't changed alignments for the various mass populations. And there's other things that we call them mad halos, halos with velocity high above the minimum and high above the average velocities. And for these halos, high-speed halos, we think that they are undergone a flyby, which is necessary for the tidal locking theory. The alignment is even higher. Some factor of 2, they are higher than the other halo populations. I'm summarizing what I told you, that we think that TTT is responsible for the initial angular momentum. It's enough. TLT can predict the spin's evolution. It can change the alignments of the halos significantly with the time. And we think that because of the velocities are anisotropic in the environment, in the cosmic web, it can also cause a correlation between spin alignments and the larger scale structure of the universe. That it's knowing this is essential for the lensing data and other things. Thank you.
Thank you. Great talk. Do we have any questions from the audience? Raise your hand or put in the chat. Can you see the Q&A question? Sam, do you see the question?
No, I don't see any question.
There's Q&A chat window. I can read the question. It's from Jay.
I've seen it. Is there a single case which can show that TLT very clearly? It's hard to see it very clearly, but we think that these mad halos are much more clear than the other ones, because if you see the alignments, TLT alignments with the vector, with the velocity, it's excess at best. 1.3 from the total random, but for the mad halos, it's 106, and this is twice that effect. We think for the mad halos it's more clearer, but because of the halo environments are too complex for calculating and visiting in the and watching it in the simulations, it's hard to see very clear results of the TLT. Gray curves on the, I assume you are mentioning this. These are individual delta L's. I told you that these curves are the average from 3,000 halo. But these are the individual ones. We just demonstrate. We just showed them in the plot for indicating that we are averaging from many processes in the with the time.
So I have a question. So you're using Illustrious. So this is this has some gas physics inside.
We only use the dark matter only simulations, but we can. It's easy to check the hydrodynamics and gas simulations.
Okay. Well, if there's no more questions, then one more question. I guess a detailed simulation on one single halo with subhalos can show the TLT more clearly.
Yes, it can, but with this with the setup simulation we are working with, the measures are something that limits the investigations. We have measures on the halos, but you are right. If we have a simulation with full snapshots, at hand, I mean that. To closest snapshot we had in the simulation, illustrative simulation, are something like 300 megayears, something like this. It's too long for watching a halo in this. But if you have more, if you have more a simulation with shorter time steps, you can follow a halo in. You can follow two halo that orbits around each other and see the TLT results clearly. I haven't yet checked that, but it's true. Yes, we can see that. We can check that.
Okay, thank you. And that brings us to the end of this session. So I'd like to thank all of the speakers. And so thank you. And
thank you. I'm leaving.
Yep, and just enjoy the rest of the conference. So thank you.